Hello everyone. We are continuing our lecture series based on vector analysis, and today we are going to discuss Laplacian operator and gradient of a scalar field. In the previous video we discussed del operator. We have already studied how to find derivative of a vector and also how to find partial derivative of a vector. Let's see. Now this is the symbol for Laplacian operator. How to derive this? Well, as you can see that this particular upside down triangle looks like del operator. So that means we would use del operator to understand and to derive Laplacian operator. Let's get started. We all know del operator is represented by I cap curly by curly x plus j cap curly by curly y plus k cap curly by curly z. And also this indicates that the presence of I cap, j cap and k cap tells us that this del operator is also a vector. It would behave as vector, it behaves as operator also, and it behaves as vector also. Now to find Laplacian operator, what we are going to do, we are going to take dot product of this del operator with itself. Okay, so we are going to write this del operator, the expression, and then here we have this dot to show the dot product, and then again the del operator. Now we know that in dot product, what happens that I cap only interacts with I cap, j cap only interacts with j cap, and k cap only interacts with k cap. Because we know that if you go for I cap dot j cap or j cap dot I cap, that would give you 0. Similarly, j cap dot k cap and k cap dot j cap would also give us 0, and k cap dot I cap and I cap dot k cap also gives us 0. So we need not to show all these products because we know they are going to be 0. It's only that when we have I cap dot I cap, or when we have j cap dot j cap, or when we have k cap dot k cap, that the answer obtained would be 1. Okay, so in this case we are directly going to use this formulate the results that we already know of vector product. Okay, but here we are talking of dot product, not the vector product. Let's see how we are going to open this. So directly what we are going to get, since this is dot product and it would apply between I cap, j cap, and k cap, k cap. So we have now curly by curly x into curly by curly x, and then same for y and z. Now we can represent this del dot del. As we know, usually what we do, we know that if we have a vector and we take dot product of vector with itself, basically what we obtain is a square. We often write it like this. So this means that all we obtain is a magnitude, because dot product of two vectors give us a scalar. So here A represents the magnitude. So there are two ways. Either we just mention it like this, or we write like this. Means one and the same thing. So here also, since del operator includes I cap, j cap and k cap, which means that it acts like a vector as well. So if we take dot product of this vector with itself, then we would get a scalar quantity. And then we can write this as, we can represent it as this thing. Need not to place arrow overhead, because now this means that it's simply a scalar quantity, because all we are going to obtain is a magnitude, and definitely it's going to be the square of all the components, all the magnitude of del operator. And you know that whatever is there with I cap, that is known as x component, whatever is with j cap, that is known as y component, and whatever is with k cap, that is known as z component. So dot product of vector with itself will simply give you a quantity which is obtained by summation of square of all the individual components. So this is what we are going to obtain here. All right. So this is our Laplacian operator. So this del square is known as Laplacian operator. So sometimes we use this operator as well, and this is derived simply from the del operator. Now let's discuss gradient of a scalar field. we have already studied what do we mean by scalar function and scalar field. Okay, so now let's consider this situation. As you can see in the pic, this is some scalar field, okay, represented by function phi. So we have scalar function phi, which is depending on three coordinates, which are our space coordinates x, y, and z. As you can see that this spread depends on x, y, and z. It is having some particular value of x. Like here you can see it has value 0, here it's 0 of y, and then you can see it's 1 of z, and so on. And this means the scalar function phi is spread over a region. You can see all this colored, this multicolored spread is nothing but the spread of the scalar function phi. Okay, and then we know that if at one point, usually for a scalar function we say that here as it is written that scalar function phi be associated with every point x, y, z of space. So that means if you consider one particular point phi, then everywhere this whole colored portion is basically the scalar field, the field of phi. So wherever you go, you will find phi. Everywhere it's phi. So phi is spread over this entire region. And then it's associated with every point x, y, z of space. That means it is depending on x, y, and z. And here, as we have written, just you can see the way we have written that this phi x, y, z is continuous and differentiable. But the thing is, whenever we write any function, be it scalar or vector, if you write anything between the parentheses, that means that particular function depend on whatever is inside the parentheses. So here we have three variables inside the parentheses. That means phi depend on these, and all these are independent variable. See, all these x, y, z, they are independent variables, and this phi, it is dependent variable. No one is controlling x, y, and z. They will change on their own. So they are independent variable. They can change the way they want. They can change anytime. But this phi is depending on these variables. So phi is dependent variable, because we know that whenever x would change, whenever y would change, whenever z would change, phi would change. Okay. And then see, this point is saying that phi x, y, z is continuous. So yes, it is a continuous function, because continuous simply as the word we know, something which is ongoing. So here you can see it's a continuous spread over some region. You are not seeing any breaks or cuts in this curve, in this spread. So it is a continuous function which is spread over some space. And at every point, you will find the same function. You, no matter where you are, suppose you look for this particular square, you would find phi depending on x, y, z. If you go for that particular sphere, you would say again you would find phi, which is depending on x, y, z. You go for this particular square, again you are finding phi, which is depending on x, y, z. So that means this whole curve represents phi. And we also say that if, okay, at a particular point we define the function, usually we define scalar or vector function at a particular point in space, and all the region around it where you would find its effect, that is known as its field. So here, if at any particular point you say you have defined phi function and this whole colored region is its field, then everywhere you are going to find phi. And then it is differentiable function of position. Of course, it is differentiable function of position. Position means x, y, and z. All these three coordinates determine position of anything. And if we are going to differentiate phi, then we will differentiate it with respect to all three. If phi was depending on only one variable, suppose there is some function which depends only on x, that means whenever x change, phi would change, and no other variable can affect phi. In that case, what we would have done? we would have found derivative of phi with respect to x, and we would have written d phi by dx, because this is the complete dependence. Phi is totally depending on x, no other variable. But what's the case here? The case is different here. How? In the sense that here phi is depending on not only one but three variables. Three different variables, which are three coordinates. So if a variable is there, then we go for derivation, simple derivative of a vector or any function. But if more than one variables are there, then whatever your function is, you have to go for partial differentiation, because you cannot say that phi is completely depending on x or phi is completely depending on y or z. No, phi is depending on all three. If any of these change, phi would change. Even if your y, z are not changing, only x is changing, phi will still change. If two out of these three are changing, phi would still change. If all the three are changing, phi would still change. So that means phi is depending on all these three. So you cannot take derivative. Instead, you are going to take partial differentiation. So you would say that you have to find curly phi by curly x, curly phi by curly y, and curly phi by curly z. And the summation of all these three would give you the actual change in phi. Alright, so these x, y, z are independent variable. And now, of course, in the beginning, initially, you would have some value of x, y, and z. But after some time, they are going to change. So suppose x, y, and z, they change to x plus dx, y plus dy, and z plus dz. So now they have changed. So we know phi depends on these three. So if initially we had function phi, then now if all these three coordinates have changed, so phi would also have changed. So we say that scalar function phi changes by d phi. That means now it becomes phi plus d phi. Now what we are concerned with, what is this d phi? What is the exact change? And that exact change is always denoted by d phi, because it shows the complete change in phi due to all the three. And then there's one more thing that we are saying corresponding to displacement dr. It depends on the direction of displacement. When x, y, z are involved, that means all the three coordinates, which are the position coordinates, the space coordinates, they are included. Then instead of always mentioning x, or you can say dx, dy, dz, we go for a common vector, which is r. R represents all the three components of space. As we know, we can write r as xi cap plus yj cap plus zk cap, and it is a vector. But this vector is often used because it includes all the three components, all the three directions are there. And we know the world is of 3D, the world we live in, at least for now, we know that it's three-dimensional. So all we need is x, y, and z coordinates. So if there would be change in r, we would denote it by dr, and definitely it would be change in x, which would be dx, and then dy and dz. Of course, dr would again be a vector. Now let's see how can we relate it with the actual formula that we are going to derive, because we are concerned with gradient of scalar field. So let's see what is that. Now the total change, whatever is happening in phi, we would write it as curly phi by curly x dx plus curly phi by curly y dy plus curly phi by curly z dz. Of course, we know we have included these three terms. We know why we have included, because phi is depending on x, y, and z. So if it depends on more than one variable, so we have to take partial differentiation, because we cannot say that phi is depending on one particular variable. It is depending on x partially, y partially, and z partially. So that's why it is there. And then we have multiplied with this dx, dy, dz. Now there are two reasons why we have included this dx, dy, and dz here. One thing, which is the simplest, and I always say, is that we have to equate the quantities on both the sides of this equal sign. As you can see, if we had kept just curly phi by curly x and curly phi by curly y and curly phi by curly z, then we cannot say that the two sides are equal. But since we have multiplied now, so we can say that okay, these end up cancelling out each other and we are left with curly phi, curly phi, curly phi, which would add up to give us the d phi. That is the simplest explanation. But the main reason which I would say is that x is changing on its own. As I've mentioned that these x, y, z, they are independent variables. Independent variables. They are changing on their own. So we have to show how much change is there in all these three. And since they are changing independently, there is no partial dependence on any other variable. So we will show this change as dx, dy and dz. We have to show that how much x is changing, it's dx, how much y is changing, it's dy, and how much z is changing, it's dz. Now what we are going to do is simply we are going to play with the mathematics. Now I have introduced this I cap, j cap and k cap here. I cap multiplied with this curly phi by curly x, and the same procedure for all the other two. Why? Because we know that I cap is always associated with x direction, x axis, j cap always with y, and k cap is always with z axis. This is the convention, the standard convention that we follow. And then this dx, dy, dz, again I have mentioned it as dx I cap and this thing. And then I have put this dot product in between. What's the reason? That now you know it's dot product, and in dot product I cap will only interact with I cap, and so do j cap and k cap. So if we actually take the dot product, we end up with this thing. Okay, so this is just the other way of writing this step. Now let's see what do we have next. Now what we can do, this phi is simply a scalar function. You remember we started with phi, which is a scalar function. We can write it outside the bracket and we can just club this I cap curly by curly x together. And this definitely gives us the dr vector. And now what is this term? You know this? It is del vector. So we are going to write this del phi dot dr. So this dot is really important because it actually indicates dot product. Usually in mathematics when we solve, we don't give that much importance to dot. Sometimes we put dot while multiplying numbers, sometimes we just ignore it. And that's the reason that whether it is there or not, we are simply going to multiply. But in physics, in vector analysis, there are different types of product. One is just simple multiplication, one is dot product, another is cross product. So there are different type of products. So if you ignore dot product, then that is a big blunder, because this simple dot tells the whole story, that what you are actually doing. All right, so now this del phi, and remember there is no sign in between because phi is simply placed here. It is not having dot product with this whole quantity, this del operator. As I told before that this del operator is just an operator. In itself it is incomplete because it simply shows I cap, j cap, k cap. Okay, the directions are there, but this curly by curly x means partial differentiation of something with respect to x and y and z. But of whom? Partial differentiation of what? That is always missing in del. So del always waits for something. So anything can fit here. Any scalar or vector can fit here. So right now we are fitting a scalar here. See, this scalar was nicely sitting at all these places. It's simply multiplying, or you can say that you are just finding partial differentiation of phi with respect to x, y and z. There is no dot product, there is no cross product, so that's why we are just going to write del phi dot dr, because obviously yes, this second step was including dot product. And now This del phi, we call it grad phi, and this is the quantity which is known as gradient of a scalar field. Okay, so all in all, what we are left with, we have d phi is equal to del phi dot dr. So always remember that this del phi, this del operator is there, and whenever another quantity is along with del and there is no sign in between, always remember that that quantity would always be a scalar. Always remember, if you have placed any quantity along with del operator with no sign in between, see, there is no sign, nothing is there. So in that case, this particular quantity is scalar always. And whenever this thing happens, you say that you are finding gradient. So the word gradient itself means that you are finding gradient of a scalar field. Whether you mention scalar, gradient of a scalar, or you simply say gradient, that would give other person the idea that yes, the quantity which is being talked about is a scalar quantity. Because we cannot have anything like this. This is unacceptable in physics or in vector analysis. You cannot have a vector quantity along with del operator with no sign in between, because that doesn't make any sense. When we have two vectors, either they should be related with dot product or with cross product. And if both are not there, that means that relation is totally invalid, meaningless. Okay, so this thing is meaningless. Never do this. So, but always remember that whenever del is there along with something without any sign in between, then that particular quantity is always a scalar, and we call this thing gradient of a scalar field. So you have to remember this. In this particular video, we have just talked about how do we derive Laplacian operator and how do we obtain this gradient of a scalar field mathematically. So this video was totally mathematical in nature. We have not discussed any significance or the physical meaning of this gradient, and that we will do in the next video. So in the next video, we are going to discuss the physical interpretation of this grad phi. What does this actually mean in physical world? What is, if you have any scalar quantity, what do we actually mean by having a gradient of that quantity? Okay, so in the next video, we'll study that. Thank you.